T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop. Falcon 9 to the towers. GC moved.
We're Team Rocket Power, and I'm Nicole Lee, and we also have Kai Kawe, Ben Neff, and Joey Nelson. We're really excited for this opportunity and are grateful to you for taking the time to watch our presentation today. Although we're not rocket scientists, we rock at being scientists and are fascinated with space. We recognize that we're not experts and are only covering a small part of a very large field, but we are comfortable with our model and the assumptions that we've made. Our objective is to model a landing control system for a SpaceX rocket. The landing system is designed to control altitude and descent speed through the payload delivery. Rockets are used for military, research, spaceflight, and rescue, but they typically only fly once and are very expensive. Currently, the one-time cost of sending a rocket to space is approximately $500 million to $1.3 billion per launch. The goal of companies like SpaceX is to reduce costs to about $83 million per launch. Just recently, SpaceX successfully launched and landed their Falcon 9 rocket at sea. This opens many possibilities for the future of reusable rockets, which will save many companies money and time.
We designed a PID controller that responds to three major disturbances. 1. Changing air density in the atmosphere. 2. Changes in the force of gravity. And 3. Changing rocket mass due to fuel consumption. By adjusting the thrust, we can ultimately control altitude, velocity, and acceleration. The PID controller needs to limit acceleration to under 6 Gs and land under safe conditions. The theory behind our controller is based in force balances. This force balance allows us to take into account the changes in gravitational acceleration, mass, and drag force to ultimately control thrust.
After modeling the system, we created a simulation for our rocket and did a step test. Using a few set points, we fit at FOPDT parameters and then optimized the controller for the best tuning parameters. Initially, we modeled the rocket to reach a set point of 200 kilometers, that's low Earth orbit, but we found that it built up a lot of air, so we changed the set point from to a single flight path instead, which took into account several different parameters, such as putting a limit on the acceleration, altitude, and time. In regards to stability, fuel depletion makes hitting a set point impossible for extended periods of time. Because there is no stable open-loop solution, we chose to look for stability along the chosen flight path. Controller stability limits were found by trial and error. Certain values of Kc over 10 and under 0.4 were found and result in unstable ascent paths. For descent, Kc values were only stable between 0.7 and 1.5. Stability issues were overshadowed by physical and material limitations, such as limited acceleration.
In conclusion, an optimized flight path is much easier to work with under realistic constraints. Static set points are slower to retune, lead to dangerous operating conditions, and offer poor altitude control. A flight path is important and should be considered in future work. For future work, we recommend optimizing the flight path to be used with a better PID controller. We also recommend implementing valve control to better simulate fuel usage, and pitch and yaw controls. With this system, a logic controller may yield better results than a PID and should be further considered. Thank you for your time.